Hi ladies and gentlemen, this is Mr. Green and we are going to continue working in geometry and see if we can't make another little dent in what we're working on. We're continuing to work through Unit 3 and in Unit 3 we come across this side splitting theorem. Side splitting theorem. No, this is not telling a joke so bad that your side splits open. Nope, not that type of side splitting. Okay? We're going to be looking at something slightly different. And this is complicated, so I'm going to work several problems today, and hopefully you'll get a good idea of what we're doing. The side splitting theorem says that if I have two lines that are parallel, then it makes the triangles proportional. It makes the triangle ECD proportional to EAB. Okay? Why would this work? Well, if you think about it, I've got parallel lines. Parallel lines with a transversal, that means that this angle equals that angle. Why? They're corresponding angles. Remember that? We talked about that last semester, corresponding angles. And then this angle up here equals itself because it's reflective. Oh, I remember this sort of stuff. And this angle over here equals this angle, oops, this angle over here. Why? They're corresponding angles. So guess what? I've actually got three angles equal to three angles, and I can use the angle-angle similarity to say that these two triangles are similar to each other. That way we can say that AE is proportional to CE. Well, we can actually go a little bit further than that, because you notice that CE is a part of AC, and we go back to that plus one theorem, and what we can actually wind up with by using that plus one theorem is that AC, that little part down there, is proportional to CE, and it's the same proportion that you have if you took the other side, DB divided by B. I said AC. AC and CE, yes. D E. Have to make certain I'm doing the right things there. So what am I saying? X, Y, Z, W. I'm saying that X over Y is equal to W over Z over W. Then we can do means and extremes. This will work out beautifully. Let's try a few examples here. This one is asking which one of these proportions are we looking at here. So e.g. is this one here. That's that whole side. Wait a second. Side splitting theorem wasn't dealing with the sides of triangles. It was dealing with this little EF down here. Nope, I'm going to say nope, not that one. Okay? EF divided by FG. Well, this is sounding real possible because we did take this little portion down here divided by the bigger portion here. EF divided by FG is equal to HF. What? HF? That's the side going this. No, sorry. HF is not what we were looking at there. That one won't work. Okay? So we look at EF or EG. That's the whole side of the triangle. That's not what we were looking at there. We were just looking at the two little parts of it. So it's not going to be this one. EF, yes, that's the one we're looking at there. FG, yes, that's the one we're looking at there. IH, yes. Oh, this one has good possibilities. HG, yes, this is my answer. This is the one that would be true. True based upon side splitting theorem. Woohoo! We split the sides in half, okay? Cool. So let's look at a problem. Looking at this one, I see two numbers over here. That's going to be helpful. And I see what we're looking for, x. I found x. It's right there. But that's not what we're trying to do. We have to set this one up. 5 divided by 13, 513. 8 divided by x, 8x. And we just do our means and extremes. 8 times 13, that's 54. 5 times x, that's 5x. Divided by 5, I get 10.8 centimeters. This one is 10.8 centimeters. Cool. What if there was some reason why we couldn't measure this one? We just now found the distance on it, didn't we? Interesting approach. Let's try another one here. 2x plus 4. Oh, they're giving it to me as an expression. That sounds ugly. But I know I can use the side splitting theorem. 2x plus 4 divided by 5. That's what they got here. And 12 divided by 6. That's this other one. Means and extremes. 5 times 12, that's 60. 6 times 2x, that's 12x. 6 times 4, that's 24. Subtract the 24 from both sides. 12x is equal to 36. Divide by 12, x is equal to 3. Woohoo, we found x. That's what we were trying to do, is solve for x. But what if we wanted to find this side over here? Well, we know that x is 3. 2 times 3 is 6 plus 4 is 10 centimeters. Woohoo! Solved that problem. Okay? So let's look at this one. I will slow down for this one. I know I go fast. I do that so that it kind of builds excitement a little bit, but we can always go slow. We've got these two triangles. They're telling us that we're going to use the side splitting theorem. That must mean that we know these sides are parallel to each other. Okay? So let's look at this. We're going to take 4 divided by 14. That's what we got over here, 4 over 14. And we come to the other side, 6 divided by 2x plus 6. 6 divided by 2x plus 6. 6 times 14, 84. 4 times 2, 8x. 4 times 6, 24. Subtract the 24 from both sides. 8x is equal to 40. That means x is equal to 5. Are we done? No, we're trying to find the length of segment LP. LP is this one down here that was 2x plus 6. So I'm going to take the 5, put it in for the x. 2 times 5 is 10, plus 6 is 16. So we found that distance, 16 centimeters. Okay? I know I go fast through some of these problems, guys. What you can do is you can rewind and watch the problem over and over again. Watch me get it, okay? So I apologize for going fast. I go slow every once in a while just to make it nice, okay? So let's look at this one, another one. 4.5 x plus 3. That's what we got, 4.5 x plus x minus 3. X plus 5, 2. X plus 5 and 2. So we do the means and extremes. 2 times 4.5, that's 9. X plus 5 times x plus 3, Mr. Green, that's mean. Doing this, that means we've got to do FOIL. That's something from Algebra 1 that we have to go back and remember how to do that FOIL process again, right? Or the box method, or however we were taught. We were taught x times x, x squared. 5 times x and negative 3 times x, that's going to give me a 2x. And then the negative 3 times 5 is going to give me the negative 15. If I subtract the 9, I'll get x squared plus 2x minus 24 equals 0. And then another Algebra 2 process, we factored it. 24 boils down to 6 times 4, and I have to use a positive 6 and a minus 4 to give me that positive 2. Oh my goodness, Mr. Green. And since this is equal to 0, either x plus 6 equals 0 or x minus 4 equals 0. So x is equal to negative 6 or a positive 4. Does a negative 6 make any sense here whatsoever? Negative 6 plus 5 would give me a negative 1. I can't have a negative distance. This negative 6 is not going to make any sense whatsoever. So we take the 4. 4 plus 5 is 9. Wow, that one made sense. 4 minus 3 is 1. That one makes sense. Okay? You see how I worked through those? I apologize about the algebra. Try not to give you too much of it, but we got to make certain we keep those algebra skills nice and strong. Okay. Word problem. Oh, I hate word problems. That means I got to do some reading. There's a reason I teach math. I don't read very good. A buoy. What the heck is a buoy? Well, you know what? If you ever go out to the ocean, you'll see this little thing bobbing out in the water out there. Okay? Pointing up and down. It's bobbing up and down, up and down. That's what bobbing means. Bobbing. Going up and down, up and down, up and down. It's telling you that it's at a certain depth is what it actually does. It's got a chain attached to the bottom down here, and it's bobbing up and down up here telling you that it's at a certain depth, and that's what it's used for. It's so that boats know they can't get any closer than that because it's not deep enough for them. Okay? That's what a buoy is. But in this situation, a buoy is located 64 feet from the shoreline. Jason, our major swimmer here, goes into the water and swims directly towards the buoy. After he swims 28 feet, and I'd be a lot less than that because I'd be tired, he turns right, okay, he turns right and swims parallel to the shoreline. That's interesting. That's an important point because it's going to make a parallel line, right? He turns right again and swims back to shore, but at an angle. He doesn't go directly back to the shore. He's not coming directly back to it. He's coming at an angle to the water's edge. As he steps out of the water, Jason is 80 feet from the buoy. How far did Jason swim to return to the shore? Well, we've got this buoy sitting here, okay? We'll label that as point B. And we get Jason, who started right here, and he swims this way, right? Well, how far was this? This was 64 feet. But he only goes 28 feet, right? So what's this distance here from where he swam to there? Well, 64 minus 28 would be 36 feet. I did that math in my head. When he gets to here, he turns right and he swims parallel to the shore. Well, we need to make certain that we draw the shore in here too. Okay? So we got the shore like that. And we get him going this way. And then he turns right again. It didn't tell you how far he swam, he just turns right again. And he comes at an angle back down here to the shore. And he exits right there. But when he exits, the distance from the buoy to where he is 80 feet. Wow. You know what? We could set up a proportion here. We could say that this one is x, and this one up here is 80 minus x. And we could actually work this out with our proportions, right? And that's what they did here. This one is 80 minus x, and this one is x. And so they say 28 over 36, 28 over 36, x over 80 minus x. Woohoo! And then when we multiply this out with our means and extremes, x times 36 is 36x. 80 times 28 is 22,040 minus 28x. I got to get my variables on the same side, and so they're going to subtract the 36 and give me 64x over here. And they subtract the number and get negative 2240 over here, and then they divide by negative 64, and we wind up with 35 feet. That means that this distance here is 35 feet. Everyone see how I did that, how I set that up? Wow, well that actually could have some bearing to real life. Now, a corollary is a statement that we make that is similar to something that we've already done. Now, corollaries are typically proven, and I think that if you look in the lesson, they do prove this one, okay? But basically it says that if I have more than two parallel lines, then it divides all of these sides proportionally. And that's what we're going to be looking at here. It's kind of it goes along with the other one. So what are we looking at? Let's see if this is going to work for me. I don't know if it will or not. Nope, it doesn't. Okay. So what they're asking is the two proportional corollary comes back and tells you that KL. Well, where's KL? KL is this distance right here. And we know that's going to be proportional to this one over here, JK. Well, the side that's the same side on the other side over there is going to be G or HG, and the side that would be proportional to is IH. So we use this one, this one, this one, and this one. Okay? Well, let's try something a little different. What if we said KL, this little side here, and then we looked at the whole thing, JL. JL and KL. Well, in that situation, we need to look at this little one over here, which again was HG, and we need to look at the whole one there, IG, IG, and HG. Woohoo! We're getting these. We're going to get all three of these written down. Okay? Next one we're going to look at is JK, which is the little bitty side here. JK. Well, the one that's same over here is going to be HI or IH. So we're just going to mark those two out. Okay? Over here we're looking at JL, the long side again, and IG. Mark out, mark out. Those are the three proportions that this corollary is giving you that would be true. Okay? You would use them at different times. Here's some problems with it. I've got, well, I can see I've got three parallel lines. See the little marks here saying they're parallel? I've got X for this one, I've got 8 for that one, I've got 10 for this one, I got 20. I could say that 8 divided by X is equal to 10 divided by 25. Okay? 8 divided by X, 10 divided by 25. Means and extremes. That's going to be 10x is equal to 200 or x is equal to 20. We found it, 20. Woohoo. Another one, okay? Here I've got some, well, it's kind of difficult to see, but they're telling me from R to P is 32, and they're wanting me to find R to Q, this distance right here, right? But they told me that M to N was 20, and they told me that M to S is 6. Well, we don't, you know what? We're looking at the whole distance here, so I'm going to look at the distance from M to O as 26. I just added them together. That's pretty easy to do, isn't it? So I've got 20 divided by 26 is equal to x divided by 32. And then I do means and extremes. I get 26x is equal to 640 divided by 26. I get 24.6. And so x is approximately 24.6. Where'd they get that from? I don't know. 24.6. That's what our q would be. Okay? Let's look at another example here. Marcus leaves the high school and drives along Union Avenue to get to the library. Where's the library? Here's the library. And where's the high school? High school's down here. So he's leaving here and he's going this way. He passes the football field, which is 2.5 miles further from the high school than it was in the library. Okay? Based upon this information in the figure, how far did Marcus drive? Okay. To get to the library. While driving, he passes the football field, which is 2.5 miles further from the high school than it is from the library. Well, they're showing it down here that if this is the x distance here, this one here is going to be x plus 2.5 miles. Okay? Now the interesting thing is they're over here on this other side, they told you that this distance was 2 and that this distance was 4. I think we can set up our proportion. Okay? And it's going to be simply stated as 2 divided by, oh, I remember this problem. This one is actually 4.25. 4.25. They miswrote the problem once. Okay, so this is 4.25. So they get 2 over 4.25 is equal to x divided by x plus 2.5. And when you do your means and extremes here and work it out, you get approximately 2.2 miles. Marcus drives the distance from here to here, which is what we were looking for. So we found out what x was. And so this one here is going to be 4.7 miles, and this one's going to be 2.2. And so it's going to add together to give you 6.9 miles. Okay? Real world situations. Isn't that interesting? Okay, well, this is Mr. Green, and this has been another in our series, right? So I do appreciate the fact that you do tell me that you're in geometry and what section of the geometry course you're in. It helps me find your information quicker. And I look forward to seeing you next time.